In 1871, Charles Darwin sat down to write about the single feature of the human body that embarrassed him the most as a scientist. Not our brains, not our thumbs, our skin. Specifically, the fact that it was mostly bare. Darwin, who had spent decades cataloging an animal kingdom absolutely covered in fur, feathers, and scales, could not come up with a satisfying reason why his own species had wandered off and misplaced most of its body hair. He guessed it might have something to do with sexual preference, early humans simply finding smoother mates more attractive over generations. He was, by his own later admission, not especially confident in that answer. He had, in fact, no idea. He was not alone in that confusion for very long, relatively speaking. Roughly 130 years later, a team of geneticists ran the numbers on human lice DNA and stumbled onto a timestamp for exactly this event, a discovery that would have made Darwin's head spin, assuming Darwin had any spare hair left to spin with by that point in the metaphor. That didn't answer the question either, not fully. It just moved the mystery to a more precise moment in time. This is the part of the human story that gets almost completely skipped over, because it's genuinely one of the strangest, least explained decisions our own biology ever made. Out of roughly 5,000 species of mammals on this planet, nearly all of them wrapped head to tail in thick insulating fur, humans are one of a tiny handful that have simply given most of it up. Elephants did it, rhinos did it, whales did it, eventually, in their own extreme way. And somewhere in the last few million years, so did we, for reasons science is still not finished arguing about. The honest answer involves a sweat gland system 10 times denser than a chimpanzee's, a genetic clock hidden inside human lice that scientists can actually read like a calendar, a running-based survival strategy that may be the real reason you're capable of a marathon at all, and one specific skin gene that quietly reveals almost exactly when our ancestors' skin was first exposed to the sun without any fur protecting it. So let's actually dig into why ancient humans lost their body hair, because the trail runs through evolutionary biology, forensic genetics, and a surprisingly competitive field of scientists who have spent careers arguing about a topic most of us have never once stopped to think about. Let's start with the mechanism itself, because understanding what your body actually did is the key to understanding when and why it happened in the first place. A 2018 study comparing hair follicle density across humans, chimpanzees, and macaques found something that immediately upends the usual mental picture of a furry ancestor versus a bald descendant. Humans, it turns out, have essentially the same density of hair follicles as chimpanzees. We are not, follicle for follicle, less hairy than our closest living relative. The difference isn't the count, it's what each follicle is doing. Somewhere in our evolutionary past, the genetic signal that tells a follicle to grow thick was switched off across almost the entire body, so that follicle now produces a nearly invisible, extremely fine strand called vellus hair, instead of the thick, pigmented terminal hair that covers a chimpanzee from head to foot. The same number of follicles, a completely different output. The leading explanation for why that switch got flipped centers on a single, extremely practical problem: temperature. Specifically, the problem of a body that was starting to work a lot harder than any primate body had worked before. That same 2018 research, alongside decades of work by anthropologist Nina Jablonski, points to the evolution of eccrine sweat glands as the real driver here, and the numbers are genuinely startling. Human eccrine sweat gland density is, on average, 10 times higher than that of chimpanzees and macaques, whose gland density is, strangely, almost identical to each other. Chimpanzees have sweat glands, but nowhere near enough of them, and a coat of fur sitting on top of the skin traps heat and moisture exactly where you don't want it trapped if your entire survival strategy depends on staying cool. Humans, by contrast, evolved a tenfold increase in cooling capacity, densely packed across nearly the entire body, capable of releasing heat through evaporating sweat at a rate that puts almost every other mammal on Earth to shame. And this wasn't a cosmetic upgrade. This was, very plausibly, a survival requirement, tied to one of the strangest hunting strategies any animal has ever developed. Humans are what's called persistence hunters, capable of tracking an animal at a steady, sustainable jog for hours at a time. Not because we're fast, we are embarrassingly slow compared to almost anything we'd be chasing, but because we can cool ourselves down while running, and most animals simply cannot. A gazelle can outrun a human easily over a short distance. It cannot outrun overheating. Eventually, in the heat of an open landscape, it collapses from heat exhaustion while the human, dripping in sweat but still moving, simply catches up and finishes the job. Thick body hair in that specific context isn't just unnecessary, it's actively dangerous, a built-in insulating layer working directly against the one biological advantage that may have let a slow, weak, weaponless primate become an apex predator on the African savanna. Now, here's where I have to be straight with you, because this is the genuinely frustrating part of the story for anyone hoping for a clean, satisfying timeline. We have no fossilized skin. Hair and skin decompose long before bone does, which means paleontologists cannot simply dig up an ancient human and check how furry the body was. Everything we know about when this actually happened has to be reconstructed indirectly, through genetics, through comparative anatomy, and through a handful of extremely clever forensic workarounds that scientists have developed specifically because the direct evidence simply doesn't exist and never will. Which brings us to the lice. In 2003, geneticists Ralph Kittler, Manfred Kayser, and Mark Stoneking took an approach to this question that sounds, on paper, almost too strange to be real science. Human head lice and human body lice are closely related, but genetically distinct populations, and crucially, body lice can only survive by living in clothing, laying their eggs in the seams of fabric pressed against skin. No clothing, no body lice. This means the moment body lice genetically diverged from head lice is very likely close to the moment humans actually started wearing clothes regularly enough to give this new parasite somewhere permanent to live. A later, more sophisticated statistical reanalysis of the same lice genetics, published in 2010, refined the estimate and placed the median divergence date at roughly 170,000 years ago. Think about what that number actually implies. If humans needed clothing roughly 170,000 years ago, that strongly suggests our bodies were already substantially hairless by that point. Bare enough that the African nights and the cooler climates our ancestors were beginning to migrate into were genuinely dangerous without some kind of artificial covering. The fur was gone well before the clothes showed up to compensate for it. Clothing, in other words, wasn't the cause of our hairlessness. It was very likely the consequence of it, invented specifically because we'd already lost the thing that used to keep us warm at night. There's a second, completely independent genetic trail that points toward a similarly ancient timeline, and it comes from an entirely different part of the body, the genes controlling skin pigmentation. Once body hair is gone, bare skin is suddenly exposed directly to the sun for the first time in the evolutionary history of the lineage, which creates immediate pressure to evolve protective pigmentation. Because unprotected pale skin under direct equatorial sun is a serious liability, vulnerable to sunburn, skin damage, and the breakdown of folate, a nutrient critical for reproduction. Geneticist Alan Rogers led a team that examined variation in the MC1R gene, a gene directly involved in skin pigmentation, and found evidence of a selective sweep, a moment when a beneficial variant rapidly took over the population, dating to approximately 1.2 million years ago. Since pigmentation only becomes evolutionarily necessary once fur stops providing that protection on its own, this genetic evidence points to a substantially earlier date for hair loss than the lice study does, potentially placing the beginning of the process well over 1 million years back, likely somewhere around the time Homo erectus was evolving into a taller, more athletic, more heat-stressed body built for covering serious distances on foot. So which is it? 1 million plus years ago, or a mere 170,000? The honest answer is that both studies are very likely correct, just describing two different points on the same long, gradual timeline. The pigmentation evidence marks roughly when the skin started being exposed enough to need protection. The lice evidence marks roughly when humans started covering that same skin back up again with clothing. In between those two markers sits an enormous, almost incomprehensible stretch of time, during which our ancestors were, by any modern standard, walking around essentially naked. Now, a quick detour through the rest of the animal kingdom is genuinely worth taking here, because it turns out humans picked a strange club to join, and the company is a lot stranger than most people would guess. Naked mole rats lost their fur almost entirely, but for a completely unrelated reason, living permanently underground in tightly regulated tunnel systems where temperature barely fluctuates, and fur simply became pointless dead weight. Elephants and rhinos lost most of their body hair because of a straightforward physics problem. An animal that large generates and retains enormous amounts of internal heat relative to its skin surface area, and fur on a body that size would trap heat to a genuinely dangerous degree. Whales, dolphins, and other marine mammals shed their fur because water conducts heat away from the body roughly 25 times faster than air, making thick fur functionally useless underwater, and replaced it instead with a completely different insulation strategy: thick layers of blubber sitting beneath smooth skin. None of these species lost their hair for the same reason humans did, and none of them are closely related to each other or to us. Researchers describe this the same way they describe wings independently evolving in birds, bats, and insects. Convergent evolution, the same rough outcome, functional hairlessness, arrived at through completely separate evolutionary pressures, in completely unrelated lineages. Humans didn't inherit hairlessness from some shared ancestor with elephants. We arrived at a similar destination through our own specific, running-based, heat-dumping, savanna-adapted problem, entirely independently. So why would evolution favor something as seemingly risky as stripping away the one layer of protection every other primate still relies on for warmth, sun protection, and defense against insect bites? The honest answer is that the advantage almost certainly had to be substantial enough to outweigh some genuinely serious downsides. And the leading theory is that it wasn't really a single advantage at all, but a tightly bundled package. A body capable of shedding heat efficiently through sweat, rather than panting, the way most mammals cool down, could sustain physical exertion for dramatically longer periods without overheating. That single capability doesn't just enable persistence hunting. Some researchers have also proposed a connection between efficient cooling and the evolution of a significantly larger, more metabolically expensive brain, an organ that happens to be extremely sensitive to overheating. The idea is still actively debated rather than settled, but if there's anything to it, hairlessness wasn't simply a hunting adaptation. It may have been one of the quiet preconditions that allowed the rest of human evolution, the big brain, the long-distance migrations, the complex social cooperation required for persistence hunting in groups, to happen at all. There's also a considerably less flattering theory worth mentioning, because the evidence for it is genuinely not negligible. Thick fur is an excellent home for parasites, ticks, fleas, and other biting insects that thrive in dense hair and can transmit serious disease. A body with less fur to hide in offers meaningfully less real estate for these parasites to establish themselves, and some researchers have proposed that reduced parasite load may have provided its own independent survival pressure favoring hairlessness, entirely separate from the heat-related explanation. It's entirely possible that both pressures, cooling efficiency and parasite avoidance, were pushing in the same direction simultaneously, reinforcing each other across an enormous span of evolutionary time rather than one single explanation doing all the work alone. Now let's talk about what happened once this was already a settled fact of human anatomy. Because the cultural reaction to it, once civilizations existed to have reactions at all, is almost as strange as the biology itself. Ancient mythology across wildly separated cultures seems to treat hairiness and hairlessness as a kind of civilizational dividing line. In the Epic of Gilgamesh, one of the oldest surviving pieces of literature on Earth, the wild man Enkidu is introduced, covered head to toe in thick hair, living among animals, eating grass alongside them, entirely outside human society. His transformation into a civilized human being is marked, quite specifically, by his shaving his body hair and anointing himself with oil after his encounter with Shamhat, at which point the animals that once accepted him as one of their own reject him and flee. Hairiness, in other words, was being used as shorthand for wildness and animality thousands of years before anyone had the faintest idea why humans were hairless in the first place, an intuitive cultural response to a biological fact nobody could yet explain. Ancient Greek and Roman standards of beauty and sculpture overwhelmingly favored smooth, hairless bodies as the ideal of youth and civilization, while excess body hair was frequently coded in art and literature as animalistic, rustic, or simply unrefined. Which means, strangely enough, that for a species that lost most of its fur somewhere between 170,000 and well over 1,000,000 years ago for reasons entirely related to sweat glands and persistence hunting, humans spent the following several thousand years of recorded civilization treating whatever hair remained as something to actively remove and manage anyway, layering an entirely new cultural anxiety on top of an ancient evolutionary one, for reasons that had nothing to do with overheating on the savanna and everything to do with what smooth skin had started to symbolize. So, why did ancient humans lose their body hair? The genetic evidence points to a process beginning somewhere over 1,000,000 years ago, likely tied to the evolution of an unusually dense network of sweat glands that allowed a slow, weaponless primate to outendure prey across brutally hot landscapes through persistence hunting alone. The pigmentation genes mark roughly when the skin underneath that vanishing fur first needed its own protection from direct sun exposure. The lice genetics mark roughly when humans finally started covering that same bare skin back up again with clothing, tens of thousands of years later. In between sits one of the longest, strangest, least visually documented transformations in the entire human story, an animal quietly shedding the one feature that every one of its ancestors had relied on for millions of years, in exchange for something considerably harder to see and infinitely more valuable, the ability to simply keep going, mile after mile, long after everything else on four legs had already given up. Whether that trade was worth it is presumably a matter of perspective. Ask anyone standing in a cold parking lot in January, and the answer may not be quite as obvious as evolution seemed to think it was at the time.